So now we're going to look at the chain rule, and what that is going to do is what happens when we have a function inside of another function. So our product rule looked at what happens when we have a function times by another function. Our quotient rule looked at what happens when we had a function divided by another function. And now we're going to look at what happens when we have a function inside of another function. Now with composite functions, in the past you've seen this notation in two different ways. This is the intuitive way, where we have g of x is a function that's inside of f of x. And I think when we write it that way, it's really easy to see that we have a function g of x inside of f of x. We also have this notation, which is a little unclear, maybe because it spells the word fog. But it also means that g is inside of f. But it's much less easy to see. So whenever I have this notation, I tend to say, well, I'm going to rewrite this like that. So when we see f composition g, we can say, well, that means g of x is inside of f of x. So what we have here in our first question is we have y equals 3x plus 2 cubed. So our function that's inside is 3x plus 2. And what is that being plugged into? Our other function, the outside function, is just cubing. So we could write that as x cubed. Does it make sense that f of g of x is this? How do we take composite functions and actually write them? Well, g of x is 3x plus 2. And so f of 3x plus 2 says wherever I had an x in f of x, I'm now going to replace it with a 3x plus 2. So the x gets cubed, so now that means the 3x plus 2 gets cubed. So that's just a little bit of review of composite functions, of function notation. We've already been dealing a fair bit with function notation with our definition of our derivative, because we're often plugging in x plus h, right? So you're getting used to that idea. Now, if we had a gut feeling about this, we might say, ooh, I've got a power. I know how to do the power rule. Power rule says I bring that number out in front and I subtract 1 from the exponents. So it wouldn't be a bad first guess to say, I think my derivative is this. Okay? Unfortunately, this is wrong, but close. But our gut says that would make sense to me. I've got my power rule. Why can't I just bring the number out in front and then subtract 1 from the exponent? It seems to be logical. In order to see what we need to do, we're going to look at this question by first multiplying it all out and then actually figuring out the derivative and seeing how close it is to this, and see if we can see a pattern for what is actually happening. So if we expanded 3x plus 2 cubed, 3x plus 2 times 3x plus 2 times 3x plus 2, and there's two different ways you could expand this. In order to get this answer, you could use what you know about the binomial theorem or Pascal's triangle, or you could multiply two of them first, get an answer, and then multiply by another 3x plus 2 afterwards. Either way, I'll save you some of the pain, and this is what you get. 27x cubed plus 54x squared plus 36x plus 8. That is something that is easy to do the derivative of because we just have a bunch of power rules, and it's sum and difference, which means we can just add them in the end anyways. So we get our derivative to be 81x squared plus 108x plus 36. This question says write our answer in factored form. So if we're going to take this and factor this completely, we notice that there's a 9 you could factor out in total. Once you take that 9 out, what you're left with is a perfect square, which can be factored as 3x plus 2, 3x plus 2. And we end up with our derivative being 9 times 3x plus 2 squared. Remember what our guess was? When we just applied the power rule, we got a 3 out in front. But it's supposed to be 9. So what's happening? How are we going to determine what needs to happen every single time? So in order for us to look at this pattern, we're going to pretend we were mathematicians and expanded all of these ones completely, then figured out the derivative and factored them just like we did before, and wrote out the answers that we found. Trust me, I didn't actually do that. Especially this one to the power 40. Expanding that completely would be really disastrous, but possible to do. And what we notice when we write it out like this is that our power rule seems to always have happened over and over and over again. But now we have something else added each time. Just like we had that extra 3 multiplied by the 3 to get the 9. In the first example, it's exactly the same kind of thing. Now we have an extra 2, which is the coefficient of the x inside, which we had an extra 3 in the previous one, which was the coefficient of the one inside. So it seems like that appears to be a pattern with those ones. But then why am I getting 6x for the second one, 4x cubed minus 1 for the third one, a 5x to the 4 for the fourth one? Yeah. So what we notice is that each of these yellow ones is just the derivative of the inside function. And the top one is also the derivative of the inside one. And our last one, which had a 3x, also was the derivative of our inside one. So then a mathematician would actually go and try to prove this in a general way, that no matter what function you use, that this always happens, and then it becomes a rule. What we do in this class is we skip that theoretical step of proving it for all things and just go to what the chain rule is. When you take university calculus, you might have a professor that decides to show you the proof for why it always works. And some of those proofs may be required on your exam. I know that on my exam, I had to prove the product law and why it always worked in general terms for my first year calculus midterm. So if you have a function and you have a function inside of a function. So I have y equals f of u, and u is a function of x as well, so u equals f of g. So here I have, in my function notation, g of x is inside of f of x. One way to write this is we have our derivative is equal to our outside derivative. So with our product rule, that meant we brought the number in front and subtracted 1 from the exponent, multiplied by our inside derivative. So we did our power rule, which was our outside function first, and did the derivative of that, and kept the inside the same. And then we multiplied by our derivative of our inside function. So this is one set of notation for this. Here we have another set of notation for this. I think this notation shows that even easier. So again, this is, and I like to call them outside and inside functions. So there's our derivative of our outside function. We kept the inside, stayed the same here. And then you multiply by the derivative of the inside function. So now let's go back and look at those ones again and see that pattern and see what I mean by derivative of outside function, inside function stays the same, derivative of the inside function. So when we look at something like 3x squared minus 7 to the 40, and I take my hands like this from the outside and I just sort of bring them in and see what function do I hit first. And as I go in, I see that I hit the power of 40 first. So I would say x to the 40 is my outside function. How do I do a derivative of something like x to the 40? That's a power rule. I bring the 40 out in front and subtract 1 from the exponent. So that's the first thing I do. The 40 comes out in front. I subtract 1 from the exponent and get 39. My inside stays the same. So when we had this right here is where I was saying that inside stays the same. Nothing happens to it. We just do the derivative of the outside part, which was bring the 40 out in front, subtract 1 from the exponent to make a 39, and the inside stayed the same. Then we multiply by the derivative of the inside function. So the inside function was 3x squared minus 7. The derivative of that inside function is 6x. Same thing happened with x to the 4 minus x to the 7. Outside function was to the power 7. That 7 came out in front, and I subtracted 1 from the exponent. Derivative of the inside function becomes 4x cubed minus 1. And our inside stayed the same while we did that. So that's where we're going to end for today as an introduction to the chain rule. We'll do more examples on this on Monday.